question asks us to compare the mechanisms of these two electrophilic addition reactions to rationalize the regio and stereochemical consequences of the reaction. Now, the mechanism for these two is actually pretty much identical. The only difference is the E and Z geometry of the starting alkene. So we'll do both mechanisms in parallel. The first thing that happens is the alkene can act as a nucleophile and can attack the electrophilic bromine molecule. That kicks out bromide as a leaving group. The only difference in electrophilic addition reactions is whether or not the alkene attacks an atom that has its own lone pair of electrons. Bromine does have its own lone pair of electrons, so we can use these electrons to bite back and attack the internal carbon of the alkene, forming a bridge bromonium ion. The same thing happens in our second example. The alkene acts as a nucleophile. That builds up too much electron density around bromine, so we kick out bromide as a leaving group. The attacked bromine does have its own lone pair of electrons, so we can use that lone pair to bite back down on the internal carbon of the alkene to form, in both cases, the bridge bromonium ion. This is the bridge bromonium ion for both of these mechanisms. This is the product that forms if the alkene attacks the bromide from the top. However, it could just have easily happened from the other side. So both of these intermediates form as a mixture of enantiomers. Bromide is formed as a leaving group here. In the absence of water, bromide would attack, open up the bromonium ion, and we get an anti-dibromide in a typical electrophilic addition reaction with an elemental halogen. However, in the presence of water, water is the solvent. Water is much more abundant than anything else in solution. And as the statistically most abundant molecule, water will be the nucleophile that opens up the bromonium ion. The water will use a lone pair of electrons to attack the more substituted carbon of the bromonium ion. That's the carbon with the larger partial positive charge. It's the more electrophilic carbon of the bromonium ion. That built up too much electron density around carbon. So we break the carbon-bromine bond and give electrons to bromine, neutralizing its positive charge. We'll draw that intermediate next. The carbon on the right will stay the same. When oxygen attacks, it will go through an inversion of stereochemistry, and so oxygen will be on a dash in this intermediate. Same thing on this side. The the carbon on the right will stay the same. It is not the one that got attacked. The carbon on the left, however, will undergo an inversion of stereochemistry. When oxygen attacks, it brings along both of its hydrogens, so oxygen will be positively charged in both cases. This is very close to the final product of this reaction. The only thing we need to do is neutralize the oxygen. To do that, we'll use more water to take one of the protons off of the positively charged oxygen, neutralizing this oxygen. This will form the final product of this reaction. Both of these products will form as mixtures of enantiomers, so we can go ahead and account for that as well. And now we can compare and contrast the products of these reactions to see how they differ in regio and stereochemistry. Regiochemically, they are the same. The bromonium ion forms and the oxygen attacks the most substituted carbon of the bridged bromonium ion. Stereochemically, however, they are different. It's hard to really see in this form, because the carbon on the right is in a different rotation in the two structures. So let's rotate this carbon on the right in this structure to make it more match the structure on top. I'm going to rotate around this bond. I'm going to redraw this product in a new rotation. Rotate it so that the carbon is in the plane. The carbon on the left will stay the same. When I rotate the carbon into the plane, the hydrogen will take the place of the bromine on the dash, and the bromine will take the place of the carbon on the wedge. Still a mixture of enantiomers. Now, when we compare these two products, we see that the carbon on the left is the same. The carbon on the right, however, is opposite. That makes these two products diastereomers of each other.